Hi everyone. In this video we are going to look at a cone. This is a diagram of a cone. We have all seen a cone in our daily lives. We know what a cone looks like, but we want to extract the mathematical importance of a cone. When you start to study about cones, you are introduced to formulas, finding the volume of a cone, finding the surface area of a cone, and calculating the length of a cone, the slant length. This is the slant length from this vertex to this point here, because you can see from Pythagoras theorem, this is the radius of the cone, this is the diameter here, half of it is the radius, and this is the height of the cone if the cone is upright. We have different types of cone. There are not many, but we've got different types. But the ones that we are interested in is this upright cone. That is the one in which the line of axis passes through the center of the cone. Here you can be able to get a right angle triangle. So if you know H, you know R, you can use Pythagoras theorem to solve the slant height, L. We represent it by L. And we are told the total surface area is pi radius L plus pi radius square. Because of this circle here, the cone has got a circle at the base. So this is a circle. So you know the area of a circle, pi radius square. And then you find the total surface, and then the surface area, considering this length and this length here, to find its area is pi RL. And the volume of the cone is given as 1/3 pi r square h. So this we know in our elementary school. But when you start to investigate the proper importance of a cone, you can see a lot more. Let's look at this other figure here. This diagram here. This is a cone. This bigger one here. If you take a plane, a three-dimensional object is just a plane, and you cut this cone, or you slant that plane through the cone, what would you get? If you do it flatly, what would you get? Or if you cut the cone at the top of the apex towards the top, you get a circle. Basically, you get a circle. If you cut the cone here, use a plane, something like a board or whatever, you cut it here, what is left is a circle. You get a circle, round circle like this. So if you now slant that board, to say, or plane, but since I'm using the word cut, I just want to use knife. If you slant it at an angle and you cut through the cone, what would you get? You get something like this. An ellipse. Ellipse. If you take that plane, you stick the angle, and cut through the cone, you get an ellipse. If you further make that angle to be steeper and it cuts through the cone, what do you get? you get a parabola. We've studied parabolas in other videos. So, when mathematicians, they want to model something, they normally extend the idea so that they try to get a general aspects of what they are trying to model. If you now use two cones, one is upside down, that is one sitting on top of the other. The apex is sitting next to each other. From this diagram here, these are two cones. This is where they are joined together. This is the top one, this is the bottom one. And now they want to use a plane again. Yeah? You use the plane and cut through these two cones. These two cones that are now connected together through the side here at a less steep angle. What do you get? Like what we have done here, if you cut this cone here, the diagram you get is something like this. If you cut one cone, if you cut two cones, you get another diagram like this. That is what we call a hyperbola. The diagram you get is hyperbola. You cut this one here, and you cut the other cone here. What is left, you get something like this here, and something like this here, and this is the middle, yeah? And this is your y-axis. This is your x-axis here, this is your y-axis, and this is the center of the two cones, yeah? So, you get a hyperbola. We're interested in this video the importance of these figures we have derived from the cone. The next video will start to solve problems. More or less, this is just to show us the importance of a cone. So let's start with when you use a plane and you cut through this cone close to the apex, you get a circle. We've all studied circles. We know the importance of circles. They are very important, especially in the field of geometry. We use circles to derive a lot of proofs in geometry. And it comes from the cone. What if you stick the angle of the plane and it cuts again through the cone? What do you get? You get an ellipse. Ellipse. If you do astronomy, you know the importance of ellipse because the planets revolve or orbit around the sun in an elliptical format. All the planets, they go around the sun. This is the sun here, and you have, just example, our planet Earth here, Mars somewhere, Jupiter somewhere, Mercury somewhere, this is just an example, Saturn somewhere. So this is how the planets revolve or orbit around the Earth in an elliptical form. This is how they go. It's not a circular form, in this elliptical form. So in the study of astronomy and even in calculus and other areas of science, if you study about elliptical formation, is very, very important. So all this is derived, the formulas they use there are derived from this very cone. And then, if you further steep the angle of your plane and cut through this cone, you get a parabola. So what are the uses of parabola? There are many, many uses of parabola. We made a video the previous time, we stated the uses of parabola. You get parabola from quadratic equations. So there, if you do finance, You can use parabolas to calculate if your accounts of your businesses, the profits, the margins, the loss, and some other things. But most importantly, parabolas, they are used, the idea of a parabola or quadratic equations are used in the manufacture of ballistic missiles. These missiles that go up and come down again to hit targets, they use a parabolic formulas. The military use missiles a lot. Launch missiles, strike the enemy, they go up, get down, all that distance with some physics in it. But the main idea is a parabola, parabolic format they take. And this is again derived from a cone. But our interest is in the hyperbola. We want to study more about hyperbola, as I told you before. And these hyperbolas, they come in two formats. I'll mention their importance to you, why we need to study them. You have a vertical hyperbola. That is when these two cones, one sitting on top of the other, yeah? If it cuts through, use the plane, as we mentioned before, it cuts through them towards the end here, you get this type of parabola. So this is a vertical parabola. This is the center here. This is your y axis. This is your x axis. This is the center, we say C, and this is the focus, F. Because that is the main thing we're interested in studying about parabolas, is because they have a focus point. So how is that important to us? Things that are made for our eyes, like glasses, lens, contact lens, televisions, monitors, a lot of them, telescopes, microscopes, are all made with the idea of hyperbola behind it. They use hyperbola calculations to make all these things I've mentioned. Your lenses, if you have problem with your eyes, the contact lens, your television, your monitors, your screen, all the way the screens are designed, they use the focus, because for you to see something, it must be focused first. For your eye to be able to see something, they need to find the focal length. That is what your eye is able to see. So these hyperbolas, they use this idea of focal length for our eyes, and from there they are able to make the monitors, the screen, the lenses, microscope, telescope, television. And they have other uses as well, like satellites. Satellites use both hyperbola and hyperbolic functions. We shall do hyperbolic functions later on in a different video. The satellites use this idea, this concept derived from the cone, hyperbola. And if you look, buildings that have cooling systems, especially those buildings that have nuclear plants in them, to produce energy, nuclear plants to produce energy, those plants that produce electricity, energy. There are cooling systems there. Those buildings are designed like a parabola. because of the importance. Sorry, I designed like a hyperbola because of the importance of the hyperbola, the mathematical importance of hyperbola. And even if you have chance to go to France, you visit Paris, you go to the Eiffel Tower, the way the widths are designed, those width, those length, those pillars, the way they are designed in a hyperbolic form. There's a reason for that. It has a lot of benefits. So if that is the case, we now see why it is important to study hyperbolas. And as I mentioned before, we got two types of hyperbolas. We got the vertical hyperbola. I can now erase this diagram here. I still want to leave that one for you to see. And we got a horizontal hyperbola. Let's start again. This is the horizontal hyperbola. Have your x here. Sorry for the poor drawing. Oh, you go like this. This is your y-axis. This is always your x-axis. So the focus is always where the parabola opens. If you say this is f2, this is f1, where the hyperbola opens, this is f1. And you have your center here, which is 0, 0, and we have this distance from the vertex to the center. We call it, let's give it A. Yeah? The distance from the vertex to the center. And then we have another distance here we call the co-vertex. We call it B. Co-vertex. We call it B. So for a horizontal hyperbola like this, in which case the center is at the origin, you have the formula x squared over a squared minus y squared over b squared equals to 1. This is the important formula of hyperbola. This formula is for a horizontal hyperbola. Then suppose the hyperbola is a vertical one. It's like this. It now goes up like this, and this one like this. Again, you have your focus here, F1, focus F2. You have your center here, C, 0, 0. And again, you have your, from the vertex to this point, you still have your A here. And now you have the co-vertex here, from here to here, which is B. We shall explain more features when we start to solve problems. I just want to state the formulas first. So for a vertical hyperbola like this, the formula is y squared over a squared minus x squared over b squared equals 1. Provided the center is at the origin. It's very important. If the center is not at the origin, you need to make adjustments here. You need to make adjustments with this y and x. So what's the difference? If it is horizontal, it starts with x. A is always positive, so A comes first. If it is horizontal, it's x squared over a squared minus y squared over b squared. If it is vertical, it starts with y. So what's this difference? Y, x squared, and it's always equals to 1. When we start to solve problem, then we start explain terms like the eccentricity, the directrix, because it's good when there is a problem, you explain those things. You draw them and you see where they come from, then we solve the problems. Thank you for watching.